Swayam Prabha. Digital India. Educated India.
So in the last lecture, we are looking at a generalized Markov process, which included both jump as well as continuous processes. We wrote a generalized differential Chapman-Kolmogorov equation. So now from now on, what we will do is we will look at specific cases. For example, we will first look at the jump Markov process, where the random variable that describes the system changes in jumps. Okay, it is a discrete variable. It makes changes from one variable to the other, characterizing a jump-like event. Okay, this is very relevant and important for chemical engineers because many of the chemical kinetics that we deal with can be caused in this form of Markov process. Okay, so the chemical simple master equation or chemical master equation is something we can model any jump Markov process. Okay, and then we will look at some examples going forward. So first we will start with the the differential Chapman-Kolmogorov equation, and then we will set the characteristic functions a and b to be 0. When a and b are 0, we remove all the continuous Markov process. We are left with only a discrete Markov process. So we write that so this is the differential Chapman-Kolmogorov equation for a discrete process. So here what we have is, we have the rate of change of the transition probability, given that at time t prime and state y, what is the likelihood that in the next time interval t, this will reach a state of z. So that is given by integral over many possible intermediates between x. So we say that, given the system is at y at t prime, it can jump to a state x comma t. Okay, and then it's possible over many intermediate values of x. So in a way, it kind of tells you the rate of generation of the rate of increase in probability and minus rate of decrease in probability. That is basically a net probability current that changes this. Now, so here we assume that x and z and all of them are actually continuous variables, but now we are specifically talking about discrete variables, so we can change the notations a little bit differently. What I would like to do is, I would like to change this variable z as n, y here as n prime, and x as m, and then this integral that we used to have, if you recollect, this integral was defined such a way that the modulus x minus z is larger than some sigma. This can be now replaced with summation over m. Okay, so this integral in dx over many jump events can be written in terms of sum over several m values. Okay, so this z is now written as n, this y is now written as n prime, the intermediate, the condition state, and then this intermediate state x here is replaced with m. Okay, so with this changes, and of course this integral with the summation. So with this we can write dou p by dou t, z comma t becomes n comma t, and y comma t prime becomes n prime comma t prime. Okay, I'm just only changing the variable, nothing else. Then on the right hand side, this integral is now written in terms of sum over all possible m. So what these equations basically means is that if I look at time t prime and time t, let's say that state is at n prime here. Okay, the state is conditioned at n prime at t prime. We are asking what's the probability that the state will be found at time t at n. Okay, so let's say n is somewhere here at time t. Okay, so we are looking at what's the probability that the state will jump from n prime at t prime to n at time t. Okay, so now this rate is given by these two terms. So if you look at this term basically tells you that this state can actually this basically tells you the probability that the state is found at n comma t, given that it was n prime and t prime. And suppose if this state jumps to something else, okay, so let's say this goes to some m, this would be a loss. Okay, this system during this time there may be a certain number of states being in n comma t can jump to some other m. So that's what this flux is. This is like a concentration term or the present state probability, and making a jump to some other state. So that means the probability current, the probability rate is changed, is decreased because of these jumps. Okay, so this is like a decay process. It's like a loss term. But also there are states which can actually come from here, come to this, where the system actually can go from here to some m, and then from here to here it can jump. Okay, so that is a net positive current. Okay, so that's what the first term is saying. What we are saying is, given the state is at n prime t prime, there will be many possible m states like this. It first jumps here, and then from here it makes a jump from m to n, and there are many possible m. So both the rate of increase in probability as well as rate of decrease in probability, both of them can go over many possible such m values. Okay, so we are basically looking at how many events are happening such a way that the state is destroyed by jumping into another event, and how many states are created by jumping from another intermediate state to the current state. Okay, so that's what the physical meaning of this equation is. This sum over m means there could be an infinite number of intermediate states over which the states can jump and then leave. Okay, essentially this is basically writing a mass balance kind of an equation, but here we are writing a probability balance. Okay, and the notations may be a little bit confusing because we are denoting the condition variable and then also the intermediate variable, and so that may be a little bit complicated, but if you understand the physics of, the physical aspect of this problem, then one can make sense of this equation. So now what we can do, so this is going to be our kind of governing equation from now on. And we can see that for a given problem, this terminology, this functions can be defined, those can be substituted, and this equation can be solved. So what I'm going to do is I'll take a very simple chemical kinetics equation for which we know the analytical results also. We use this chemical mastery equation formulations and then solve this same problem so that we can compare with the deterministic approach. So the problem that we can solve is something like a first order reaction A going to B, okay. And so here the random variable to describe this, so okay, so let me say that this is basically a reaction vessel, okay, batch reactor, and I have molecules A and molecules B. These are present, well mixed, constant temperature, constant volume reactor, batch reactor, and A is reacting to B. Your task is to find out what is the concentration of A and B as a function of time, okay. So now typically we solve this problem from a deterministic framework. We write rate of change of A is equal to some K times CA, and then you will get a first order ODE, and then you will solve with an initial condition that we know. But now what we are saying is the same problem we wanted to look at from this Markov process point of view, thinking about this reaction A to B is a stochastic process, is a Markov process that happens with a certain probability of going to A to B. So now what we are saying is the state variable then X can be number of molecules of A and number of molecules of B, okay. There are two variables that we can specify, but in this case the molecularity is 1 A gives rise to 1 B, and I'm going to also define this Na naught and Nb naught. These are initial conditions, okay. So I can also say that the total initial number of moles is this, and this is a conserved quantity in this case, okay. So this also means that Na plus Nb at any time should be equal to N naught. By this mean, we don't have to really track both quantities. If I know one quantity, if I track one quantity, the other quantity can be obtained from this, okay. So this two variable problem simply becomes a single variable problem. So the state of this reaction can be described by the one single random variable, which I call this number of molecules of A at any time t. If I know that information, I can very well get Nb also. So therefore, we can write this equation for a single variable process. All right. So then, so we have found that N here is going to be my Na. So for the reaction A to B, this Na basically means number of molecules of A, okay. So that we have specified. And then what we want to do now is, what about these terms, okay. So remember, these are the transition probabilities, that the rate at which, given the state is at M and T, what's the rate that it will go to M, okay. So let me look at the definition of W, what we have done before. So we said that in the limit delta T going to 0, P of x comma T plus delta T Z comma T over delta T is given as so this is the way that I defined the transition probability when we looked at the derivation of differential Chapman-Kolmogorov equations. So now what we want to do is do the same thing, but apply for this discrete case So X is M, Z is N, so this is what we are using here. So this is our original definition. I am just changing the variables X to M, Z to N. Then I have got a discrete definition of the jump probability or the transition probability. So what this is saying is, from t to t plus delta t, when I look at a very incremental time delta t, what's the probability that it will go from n to m? And in n and m can be finite quantity. It need not be very infinitesimal quantity, because n and m are discrete variable here. Okay, and that is this function. Now, when I look at this problem, that A going to B, now we have to make an assumption that what is this jump going to be? When I am in N, what is going to be M? So when you look at this kind of reaction A to B, we have to now qualify two things. One is we have to justify that this is a Markov process, and then we have to say that this is also jump Markov process. These are the two things we want to know before we apply to this equation. Okay, this equation is valid for discrete Markov process. Okay, these are mathematical formulations. Now I have a chemical problem that A is reacting to B. So I want to justify that this is a Markov process and also it's a jump Markov process. Okay, so I can say it's a Markov process because if I look at this reactor at any point of time t, if I have n number of molecules, okay, in the next time interval, the reaction rate will depend only on the number of molecules currently present. It does not depend on what was there 2 times step behind. That is irrelevant. Right now, the next time moment, how many molecules are going to react depends on only how many molecules are present at this point of time. So you're all there. If I ask a question, the probability who will answer this question depends on how many students are sitting here. Doesn't depend on who were sitting in the previous class, right? Something like that. So here, the reaction kinetics is determined by the number of molecules present at time t. That pretty much justifies it can be modeled as a Markov process. Okay. The second thing is jump or the discrete nature of the process. So here the number is taken as an integer variable to describe the reaction. What we can also say is that over a time period delta t where the reaction happens, we will assume that only one molecule can make a jump by decreasing one. Okay, only one molecule actually jumps from A to B. So therefore n becomes n minus 1. Okay, it makes a discrete jump by one molecule at a time. Okay, so we say that n goes to n minus 1. It can either be at n or it can change to n minus 1. That's the only option it has for this kind of process. Okay, so what I'm saying is I ask a question to this classroom, all of you can remain silent, nobody answers the question, or one of you can answer the question. We are not expecting simultaneous answering of many questions. Okay, so that is the time segment or the time limit we are looking at, where one molecule is reacting, one student is answering. Okay, and then since we are talking about integer number, we can also justify it is a discrete or a jump Markov process. So therefore, this is important. Number of molecule can decrease by n minus 1. It depends only on the number of molecules at this time. It doesn't depend on what was there before and in the past. So with all that justification, what we can do is now we can write here. If I look at this statement, what might happen is W can become so even though I said that there are many possible m values, for this reaction, if it is n, it can only become n minus 1. It cannot go to n minus 2, it cannot become n minus 3, or it cannot become n plus 1 and n plus 2. The only possible mechanism of reaction is m becoming n minus 1. Okay. So similarly here what happens is that for this reaction m can only be n plus 1. So in this case the state can be at n plus 1 and that can make a jump to n. Only these are the two options we have got. Okay, when I have, so I was writing this, suppose I am at n, this is n plus 1 and this is n minus 1. The possible events are that either you can go this way or you can go this way. So when I look at this jump, the probability is destroyed. Okay, the probability of finding a particle at m is decreased whenever this jump happens. Whereas when the state is at n minus 1, the fact that a reaction can lead to formation of n, this is a creation of the state. So now these two equations basically going to combine only these two processes. So we are all saying that by making assumption that for a reaction like this, at any point of time only one molecule can react. In this case n is a number of A molecule. It is an irreversible reaction. A can only decay. Suppose if I have a reaction like this, then I have other possibilities. Okay, so right now we don't have that right now. Let's take a very simple case. N can only decrease by 1. So with all this, now we can actually write this equation more specifically for this problem. We want this given that the state is at n plus 1, in the next time interval it decreases to n. What that rate can be written for this problem? What would this expression be? For a chemical kinetics A going to B. Isn't this k times n plus 1? I have n plus 1 molecules and they all reacting k per unit time. So this is the transition probability for this event n plus 1 to n happen. Similarly, we want this also we want, because the state can be at n comma t and the next time interval it can become n minus 1. What is the rate of this? What's the rate of this would be? Kn, yes, just Kn. That's all. Now I will remove this conditioning of this variable because we know that what is it conditioned. So it's conditioned with respect to some initial condition. Okay, n prime t prime is something we can define based on the initial conditions. So I'm removing all this condition statement here, but remember this is a transition probability. So you can see that the general equation that we wrote becomes very simply for this case. This term basically describes n plus 1 becoming n, and this term says n becoming n minus 1. Okay. Any ideas how we can solve this equation? This is a recursive relation, right? So recursive equation. So any ideas how we can solve this? Have you seen this kind of equation before? But what you will get is you will get a set of ODE for different n values, right? So what you want is, this is a differential equation. Actually, you can actually write in terms of d by dt now. what you want is, you want to solve this and get, you want to get P of n comma t. What is P of n comma t? This tells you what's the probability of finding n. N is the number of molecules of A as a function of time. So we want to solve this to get this. Any ideas? Have you heard of this generating functions? Generating functions? Yes or no? Yes? In what context have you seen? Sorry? Have you used generating function to solve ODs or PDs? Huh? Okay. So that's what I'm going to do. I'm going to apply some sort of transformation. So I think you have seen like Laplace transform, Fourier transform, Z transform, like that, right? So generating function also something similar. Okay, generally used for this kind of discrete recursive differential equations. Okay, and the idea is very similar to Fourier transform and stuff like that. Okay, so we're going to define a function and then change the variable from n comma t to some other variable. Okay, and then do the inverse transform later on to get this. Okay, just like how we do Fourier transform for PDE. Okay, you go to Fourier space and then solve it in terms of wave vector, and then you do an inverse Fourier transform to come to a domain, time domain. Something similar we can do here. Okay. Okay, so we have, what is the system we are modeling? We are modeling a chemical reaction A going to B with rate constant K. What is initial condition? Initial condition is that number of molecules of A naught is actually specified, and you can say this is something like Na naught, and then Nb naught is 0. And in terms of probability, we can write this as n comma 0 is delta n Na 0. Okay, so at time t equal to 0, this probability is basically a delta function. Okay, where this is defined as 1 only when n equal to Na naught. Okay, so this is a way of defining the initial condition as a deterministic variable. And okay, so we got rate constant, we got the chemical equation, we got the initial conditions written also in terms of probability density. So the governing equation, okay, the governing equation is dp n comma t is equal to k n plus 1 p of n plus 1 t minus k n p of n comma t. Okay, so this is our master equation for this reaction. So now what I'm going to do is, to solve this, we're going to define a generating function g of s. So we defined a function, generating function g of s comma t as this. It is defined as sum over n to infinity, some variable s power n p of n comma t. So now what we want to do is, we want to rewrite this equation written for p in terms of g. Okay, and after that we can do an inversion and then get the p of n comma t. So that's the idea. So to see this how to be done, so what we can do is, we can actually multiply this entire thing with the s power n and then sum over, right? So we are summing over n s power n dp by dt so k is constant, so that comes out sum over n plus 1 times s power n p of n plus 1 t minus k n s n p of n comma t. Okay, so all I have done is I have taken this master equation, I have multiplied by s power n in all the terms, left hand side and right hand side, and then I have summed over all n values. So now what we need to do is we need to deal with these terminologies. Okay, so in order to do that, so first we will take this equation, the definition itself, and then we will do dou g by dou s. We take this is a function of both s and t. I take the partial derivative of this with respect to s. What do I get? I get this. Now if I multiply by s across, I get dou g by dou s and Sn p of n comma t. You can see that in the original equation that I want to deal with, this terminology that you see here is actually nothing but s times dou g dou s, right? This terminology that you see here, n times Sn p of n comma t, this is actually nothing but s times dou g by dou s. So I can deal this term with this. Now what I can also do here is I can substitute n to n plus 1. I'm just changing the variable. So here whatever I have n, I can replace this n plus 1, okay, because n is a dummy variable I'm summing over. Okay, if I write n as n plus 1, this term becomes n plus 1, this term s power n and the p of n plus 1 plus t. The reason why I write that is because if you look at this term, the first term, actually it is in that formulations. Okay, so now both this term and this term I can actually write in terms of the partial derivative of g with respect to s. And what about this? How do we deal with this? Isn't this the partial derivative of g itself with respect to time? If I take time derivative of this, then I get this, isn't it? Okay, so now this left hand side time term and the two of the right hand side time term, all of them can be now written in terms of the partial derivatives of g itself. Okay, so we have on the left hand side dou g by dou t. Sorry, it's not dou g, it's actually dg, total derivative, dg by dt is equal to k times this entire thing is dou g dou s minus k, this is nothing but s times dou g by dou s. no, I think this should be dou G dou S, because G is both function of S and T. Okay, so this is what we want to deal with now. Any ideas how to solve this equation? What is this? This is a partial differential, linear partial differential equations. Okay. Any idea how we can solve this? Huh? We are going to use a method called methods of characteristics. So we have S and T. Okay, these are two independent variables. We want to think about a variable, some other variable, where any change in S and T can be the constant value of the new variable. Okay, so those are called methods of characteristic for solving linear PDEs. Okay, so we want to define some new variable Z. Okay, any change in S and T can happen at a constant Z values. Okay, so this is called methods of characteristics. So what we will do is we write a new variable dg by dz, something like this. So G is a function of S and T, and I want to look at a new variable Z, okay, such that I can write the derivative of dou G by dou Z using this chain rule. I look at dou G by dou Z and dou Z by dou T plus dou G by dou S times dou S by dou S. Okay. Sorry, this should be, yeah, correct, yeah. So from here, this is the equation that we want to solve. We write dou G by dou T minus K 1 minus S dou G by dou S equal to 0. So now what? So this is my original equation I want to solve. Okay, and here I have defined a new variable Z so that this equation is valid. So now I can actually look at these two and compare and find what that Z should be. Okay, so Z is something I have not defined. I am expecting Z to absorb the S and T, but we have not defined what that Z is going to be. Now by writing a total derivative of G with respect to Z and then comparing the original equation that I have, now we can look at term by term what is the corresponding values here. Oh yeah, this is supposed to be T, yeah, is what you want to say. Okay, yeah. Okay, so now if you look at these two, you see that this term and this term have the same characteristic, and so this and this, so basically we see that dg by dz equal to 0. This is what I was mentioning, that any change along the z is 0, so this is one relationship. And then if I look at these terms, so here I have got dou G by dou T, this is multiplied by 1, so dou T by dou Z should be 1. And when I compare these two terms, the prefactor of dou G by dou Z should be dou S by dou Z should be equal to minus K into 1 minus S. So basically we get two characteristic equation that will tell you, if I solve this, it will tell me how Z should depend on, how Z is defined in terms of S and T. So z and t. Okay, so z is a new variable I'm defining. So here if you see up to this point, g is a function of s and t. Okay, s and t, these are two independent variables. S is something we introduced based on the generating function to replace n. So if you see from here to here, what we have done, initially we start with n comma t. Our two variables are n and t, right? Now by mapping into a generating function, I am able to eliminate n in terms of s. So we got this. Okay. Now g here is written in terms of t, not n but s. Okay. Up to this point we have got this. Now from here onwards, we have a two variable. So we want to combine. We want to have a new variable z, where both variation of t and z can be mapped into. Okay. If I can tell you an example of in heat transfer, when we do one-dimensional transient heat conduction, temperature depends on position and time. Okay. Now we combine this position and time together into a non-dimensional variable. So instead of looking at independent variation of x and t, we look at variation of one combined group. Okay, that can encapsulate the variation in both x and t. Okay, so by renormalizing, by grouping the two independent variables into one group, we can look at change of the function with respect to one non-dimensional group. Like that, here z is a function that is defined based on s and t. Variation in s and t can be absorbed in one single variable, which is z. So now by doing that, I can come up with a single equation like this. Okay, now g is written only as a function of z. And now what that z and how is it related to t and s, those are obtained from these equations. And how I got these equations is basically defining the chain rule for z and then comparing this derivative to the equation that I want to solve. I match the coefficients of each derivative. So here I match the dou g by dou s, dou g by dou s. This prefactor here must be equal to this. That's what this characteristic equation is. Similarly, when I look at the prefactor of dou g by dou t here, so this dou t by dou z should be 1. Okay, this basically tells me that z equal to t. Let me check if it's defined that way. Yeah, t is equal to z, and then if you solve this equation, you will get. No, we can just simply integrate this. This is just a linear first order differential equation. So, in fact, we can write this as. Yeah, I think I have written this notes here, so it should be. S naught is equal to 1 plus s minus 1 e power minus kt, where s naught is the value of s at t equal to 0. So what we have done here is we have solved this with respect to s as a function of z, but we know z is nothing but t, so I can replace z by t. So I got this equation. Sorry, which one? Z must be non-dimensional. Why do you say so? I gave an example. Of combining groups of terms into one. In this case, we are not making that non-dimensional. In fact, z has a time characteristics. Okay. Okay. So we are running out of time. So what I'll do is I'll stop here, and then next class I will start from. I will kind of begin from here. So right now, all you have to remember is we have a chemical kinetics, very simple chemical kinetics. Define the initial conditions. We defined this is a Markov process, discrete Markov process. Based on that, we wrote the chemical master equation for this case. Now to solve this, we use a generating function to replace the variable n in terms of s. By doing so, we arrive at this kind of partial differential equation. And to solve this, we use methods of characteristics. tomorrow before you come to class, just read a little bit about methods of characteristics. You must have studied in mathematics course, and that these things will be little clear with you. Okay, and so we'll start from here in the next class.